Imagine you are floating in the infinite dark, surrounded by a scattering of brilliant galaxies. Spiral arms glowing like cosmic fireworks, clusters of stars burning silently in the void. Slowly, the lights fade. The galaxies grow dim, their shapes dissolving into faint smudges. And then, nothing. Just a black canvas stretching endlessly in all directions. In that silence, a question whispers into your mind. If the universe has an edge, what's beyond it? It's a question that has haunted scientists, philosophers, and curious minds alike for centuries. A question so deceptively simple that a child might ask it, yet so profoundly difficult that some of the brightest minds in human history have spent lifetimes chasing its answer. It's the kind of question that doesn't just test your knowledge, it shakes the very foundations of how you think about reality itself. But before we continue, subscribe to the channel and like the video. Picture it, you're on a spaceship traveling at an unimaginable speed, faster than anything humanity has ever built. You pass the Milky Way's outer halo of stars, leave behind the great cosmic filaments of galaxies, sail past quasars, those colossal beacons powered by black holes, until you approach what seems like the very end of the universe's light. You wonder, will I see a shimmering cosmic curtain? A glowing wall? Or will I suddenly tumble into nothingness? But here's the twist. The answer is far stranger than any science fiction tale you've read. The truth is, the edge of the universe, if we can even call it that, is not a wall you could touch, not a boundary you could fly past, not an endpoint in the way we imagine a cliff or a fence. It's something much more abstract, and much more mind-bending. To grasp this mystery, we have to peel away our everyday understanding of words like edge, limit, and beyond. We have to think bigger, not just in miles or light years, but in concepts that stretch the imagination. And along the way, we'll travel through the story of cosmic expansion, the limits of observation, and the tantalizing possibility that our universe might be infinite, or just one among countless others. So buckle in, because what lies ahead is not just a scientific journey, it's a philosophical odyssey. One that might change how you see not only the universe, but your own place within it. When we hear the word edge, our minds instantly go to something tangible. It's a word that feels familiar, almost comforting, because it's part of our everyday experience. An edge is the rim of your coffee cup, a neat, circular boundary that separates the warm drink inside from the air outside. It's the cliff face you stand at while staring down into a canyon, where the solid ground simply stops and empty space opens up beneath you. It's the shoreline where the land ends and the ocean begins. Edges in our daily life have a few common traits. They are visible. You can see them clearly. They are physical. You can walk up to them, touch them, feel them. They are definitive. They mark a clear transition from here to there, from one state to another. That's how our senses have evolved to understand boundaries, sharp divisions, lines that can be crossed, borders that have a before and an after. We live on a planet where geography constantly reinforces this idea. There are mountain ridges, fence lines, walls, riverbanks. Even our language leans on this concept. We talk about pushing something to the weight of cosmic reality. And this is important, because before we can even begin to answer what lies beyond, we have to retrain our intuition. The edge of the universe is not like the lip of a table. It's more like the shifting, unreachable line where the ocean meets the sky. When we talk about the observable universe, we're talking about a concept that's deceptively simple in words but profound in meaning. It's not the whole universe. It's not even necessarily the universe we live in. It is, quite specifically, the part of the universe we can see, or more precisely, the part from which light, and other signals, has had enough time to reach us since the moment the universe began. Think of it this way, light doesn't travel instantaneously. It has a speed limit, about 299,792 kilometers per second, or roughly 186,000 miles per second. That's unimaginably fast in everyday life. A beam of light could circle Earth more than 7 times in a single second. But in the context of a 13.8 billion-year-old universe, that speed is not infinite. That means that even though the universe itself may be vast beyond comprehension, we can only observe the portion from which light has had time to reach us since the Big Bang. Everything beyond that is hidden from us, not because it doesn't exist, but because its light is still on the way, and will be for billions or trillions of years to come, or maybe forever. Now here's where it gets slightly mind-bending. You might think that the observable universe should have a radius of 13.8 billion light-years, since that's the age of the universe in years and light travels 1 light-year per year. But that's not the case. Because the universe has been expanding all the while that the light was traveling toward us, the distances between objects have stretched enormously. This means that the farthest objects whose light we can currently detect aren't 13.8 billion light-years away in today's terms. They are about 46 billion light-years away. The observable universe, therefore, is like a giant sphere with us at the center, about 92 billion light-years across. That sphere isn't special because of our location. It's special because of our perspective. Every observer, no matter where they are in the universe, has their own observable sphere centered on them. An alien civilization 10 billion light-years away would have its own cosmic horizon, showing regions we can't see, and missing some of the regions we can. The observable universe is personal to each vantage point in space. What makes this concept both beautiful and frustrating is that it places a fundamental limit on our knowledge. We can build bigger telescopes, we can collect light for longer exposures, we can even try to detect particles like neutrinos or ripples in spacetime itself, but we cannot see beyond the observable boundary with light. It's not just a technological limit, it's a law of nature limit. The speed of light and the age of the universe work together to form a horizon that marks the outermost extent of our visible cosmos. This cosmic horizon is not sharp like the edge of a coin. There's no point where you can say, this pixel is inside, and the very next pixel is outside. It's more of a conceptual shell, the farthest light that can ever have reached us by now. Beyond that shell lies more universe, possibly infinite in extent, but invisible to us for now. And here's a subtlety that often gets overlooked. The observable universe is constantly changing. As time passes, light from more distant regions is finally arriving. In the far future, if humans or our descendants are still around, they will be able to see galaxies and cosmic structures that are currently hidden from us because their light hasn't yet reached our part of space. In other words, the edge of our observable universe is moving outward in time, but not in a way that gives us access to everything. Because of cosmic expansion, some regions are receding from us so fast that their light will never, ever reach us, no matter how long we wait. This makes the observable universe a bittersweet concept. On one hand, it's a map of everything we could possibly know through direct observation, a kind of ultimate frontier of human perception. On the other hand, it's a reminder that there is vastly more out there than we will ever see, more galaxies than we will ever count, more cosmic history than we will ever directly witness. It's a little like standing in a small clearing in a vast forest at night. You can see a ring of trees around you in the glow of your lantern, but you know that beyond that faint circle of light, the forest continues without end into the darkness. And just like that lantern in the forest, the light from the early universe is finite. It began at a certain point, not in space, but in time, and that gives us an absolute ceiling on how far our vision can reach. We live inside that illuminated bubble, aware that it is surrounded by darkness not because the forest ends, but because our light hasn't reached there yet, and theirs hasn't reached us. When you hear that the universe is 13.8 billion years old, it's natural to assume that the farthest we could possibly see would be 13.8 billion light-years away. After all, light travels 1 light-year per year, so that should be the maximum reach of our vision, right? But this is one of those moments where cosmic reality politely smiles and says, not quite. The true size of the observable universe is far larger, about 46 billion light-years in every direction, meaning roughly 92 billion light-years across. And the reason for this comes down to a key fact about our cosmos. It's not static. It's been expanding for its entire history. To understand why this changes the numbers so dramatically, imagine this. You're standing on a long, stretchy rubber track. At the far end, a friend turns on a flashlight and sends a beam of light toward you. As the light travels, you start stretching the track between you. Even though the light is moving toward you, the space it's traveling through is being pulled apart at the same time. By the time the light finally reaches you, the point it came from is much farther away than it was when it started. That's essentially what has happened since the Big Bang. The light from the most distant galaxies we can observe today began its journey when the universe was just a few 100 million years old. Back then, those galaxies were relatively close, in cosmic terms. But during the billions of years that light traveled toward us, space itself expanded, carrying those galaxies farther and farther away. Today, those same galaxies are not 13.8 billion light-years distant, but around 46 billion light-years from us. This expansion is not galaxies flying through space in the way a rocket travels through the air. It's space itself stretching and carrying galaxies along with it. This is a crucial difference. In everyday life, if you and a friend are moving apart, it's because one or both of you are traveling through space. But on the cosmic scale, it's the fabric of space between you that grows. Now, the observable universe is like a spherical bubble with Earth at the center, but not because we're in any special place. Any observer anywhere in the universe would see themselves at the center of their own observable sphere, because the limit is determined by how far light has traveled to reach them, not by where they are in absolute terms. From our perspective, the edge of that bubble is about 46 billion light-years away in every direction. What's more, that size is still growing. Every second that passes, light from slightly farther regions of the universe reaches us for the first time. But there's a bittersweet twist. Even though our observable bubble grows with time, the universe's expansion means there are regions that are moving away from us so quickly that their light will never, ever catch up, no matter how long we wait. That means there's a vast amount of the universe that will remain forever outside our reach, observationally and physically. So when we talk about the size of the observable universe, we're talking about a moving target, a bubble that's been growing since the first moment light could travel freely through space, and that continues to grow as time goes on. But it's not growing into empty nothingness. It's more like an expanding frontier of knowledge, a horizon that gradually reveals more of the cosmic landscape, even as the most distant lands race beyond our ability to ever reach them. What's staggering is that even within this 46 billion light-year radius, the numbers are almost impossible to comprehend. The observable universe contains at least 2 trillion galaxies, each with hundreds of billions of stars, and countless planets, moons, and other objects. That's 2 trillion islands of matter and energy, all suspended in the vast, expanding sea of space-time. And those are just the ones we can see. Beyond them could be infinitely more, unreachable and invisible. When you stand under night sky and see a few thousand stars, you're looking at the tiniest possible fraction of what's really out there. The scale is so immense that our language and imagination struggle to keep up. That's why the figure, 46 billion light-years in radius, is more than just a number. It's a doorway to a deeper truth. We are small, but we are part of something staggeringly vast, and the limits of our sight are set not by walls in space, but by the intertwined fabric of time and expansion. Every time you look up at the night sky, you're not just seeing space, you're seeing the past. That's because light, despite being the fastest thing in the universe, takes time to travel. Even in our everyday lives, light travel time exists, but it's so minuscule we don't notice it. The light from the lamp in your room reaches your eyes in just a few nanoseconds. The sunlight warming your face took about 8 minutes to cross the 150 million kilometers from the sun to Earth. But in the vast theater of the cosmos, these delays become profound. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes ago. Glance at the nearest star beyond our solar system, Proxima Centauri, and you're seeing it as it was more than 4 years ago. These aren't just poetic facts, they're hard, physical realities. Now, stretch that idea to the grandest possible scale. If you look at the Andromeda Galaxy, our closest large galactic neighbor, you're seeing it as it was 2.5 million years ago. The light left Andromeda back when early humans, our distant ancestors, were just beginning to experiment with tools. The galaxies you see in deep space images from the Hubble or James Webb Space Telescope. Many of them are so far away that their light began its journey billions of years before Earth even existed. This is where the concept of a look-back time comes in. The farther away an object is, the older the light we see from it. Space is like a time machine, not in the science fiction sense of hopping into a vehicle and setting a date, but in the sense that the universe delivers ancient light to us continuously. Every photon that strikes our telescopes from a distant galaxy carries with it a timestamp from its origin. When astronomers study that light, they're reading a message written in the deep past. But here's where things get even more fascinating, the limit of our ability to look back is set by the age of the universe itself. The universe is about 13.8 billion years old, which means the oldest light we can possibly receive today had to have begun its journey at most 13.8 billion years ago. Before that, the universe didn't have transparent space for light to travel through. It was a hot, dense plasma, opaque like the surface of a star. This creates what's known as a cosmic horizon in time. No matter how powerful our telescopes become, we cannot directly see farther back in time than the moment when the universe first became transparent to light. That moment occurred about 380,000 years after the Big Bang, and the light from it is what we call the cosmic microwave background. When we look at that faint glow, we are looking as far back in time as photons can carry us, almost to the beginning, but not quite. The link between distance and time is one of the most mind-altering aspects of astronomy. We're used to thinking of space as a three-dimensional grid, something you could theoretically map in the present moment. But in reality, our view of the universe is always a layered archive of history. The closest objects are the newest in our vision. The farthest objects are the oldest. There's no way to see the universe as it is right now in its entirety, because right now is different in every direction, depending on how long it took the light to arrive. Even more astonishing, the expansion of the universe stretches this light as it travels, lengthening its wavelength and lowering its energy. The result is that ancient light from the earliest galaxies has been shifted so far toward the red end of the spectrum, what astronomers call redshift, that it's invisible to human eyes. We need specialized infrared instruments to capture it. So when you gaze at a starry sky, you are actually gazing through time. The light from each point is a snapshot from a different moment in cosmic history. The night sky is not a single picture of one instant, it's a vast mosaic, stitched together from billions of years of cosmic memory. The idea of the cosmic horizon is one of the most profound concepts in cosmology, because it defines not only what we can see today, but also what we can ever see, even if we wait for eternity. To picture it, think of standing on a ship in the middle of the ocean. No matter which way you look, your view ends at the horizon, where the curve of Earth hides everything beyond. You know the ocean continues past that line. Ships, islands, and entire continents may be out there, but the planet's curvature makes them forever invisible from your spot on the deck. The cosmic light horizon is similar, but instead of being shaped by Earth's curve, it's set by the finite speed of light and the expansion of space. It marks the farthest distance from which light, or any information traveling at the speed of light, can ever reach us, no matter how long we wait. It's not just a horizon for now, it's a horizon for all of time. This is different from the observable universe we've been talking about. The observable universe is the region from which light has had time to reach us since the Big Bang, a sphere about 46 billion light-years in radius. The cosmic light horizon, often called the event horizon in cosmology, is the ultimate limit, beyond which light emitted today will never, ever get to us in the future. Why does this ultimate limit exist? Because space isn't static. The universe is expanding, and not just expanding, but expanding faster and faster due to dark energy. In distant regions of space, the expansion is happening so rapidly that even light moving toward us gets swept away by the stretching of spacetime itself. The farther away something is, the faster it recedes from us, and at some point, that recession speed exceeds the speed of light. Beyond that boundary, light emitted toward us is effectively trapped. The space between us grows faster than the light can close the gap. This is completely allowed by physics because the rule that nothing can go faster than light applies to motion through space, not to the expansion of space itself. Space can stretch as quickly as it likes, and it does. This is why the cosmic light horizon exists, not as a physical wall, but as a consequence of geometry, physics, and the nature of space-time. If we could see this horizon, it would look eerily like being inside a black hole, but inverted. In a black hole, the event horizon is the surface beyond which nothing, not even light, can escape. In our expanding universe, the cosmic horizon is the surface beyond which nothing, not even light, can reach us. We are not inside a black hole, of course, but the analogy captures the sense of finality. Currently, this cosmic light horizon is about 16 billion light-years away in terms of comoving distance. That's the distance accounting for the expansion of space, rather than the distance light has traveled. Anything beyond that limit, even if it exists right now, will forever remain unseen. The photons they emit in our direction today will never arrive, because the expansion of space will always outrun them. This means that the universe, as far as our potential to interact with it is concerned, is actually much smaller than the infinite or near-infinite expanse it might truly be. Our cosmic light horizon defines our ultimate island of reachability in the grand ocean of space. We may be able to observe some galaxies today that are already beyond this horizon. Their ancient light left billions of years ago when they were closer, but by now they've been carried so far away by expansion that they're permanently out of touch. In the far future, those galaxies will fade from view entirely, leaving only the local group of galaxies bound to us by gravity. In a sense, the cosmic light horizon is bittersweet. It's a reminder that we live in a dynamic, ever-changing universe, where the visible sky is not fixed but shrinking in what it can ultimately reveal. Yet it's also a poetic boundary, a reminder that there is more beyond than we will ever see, a vast and unreachable expanse that hints at the enormity of existence. When people first hear the term observable universe, it's easy to mistake it for the entire universe. The name feels all-encompassing, as if it's the whole story. But that's not the case. The observable universe is simply the portion of the cosmos that we can access with light and other signals. It's the bubble of visibility around us. Beyond it, the universe almost certainly continues, possibly without end. The idea that space might keep going beyond what we can see can be hard to wrap your mind around, because in our everyday experience, boundaries are real and final. If you're in a walled room, you know the room ends at the wall. If you're on an island, the ocean is a physical boundary beyond which you need a boat to travel. But the edge of our observable universe is nothing like a wall or an ocean shore. It's more like the limit of your vision in a thick fog. The world beyond is still there, but hidden from you. The reason for this invisibility isn't that something physical blocks our view. It's because light from those farther regions hasn't had enough time to reach us since the universe began. Think of it as an ever-expanding sphere of awareness. The moment the universe was born, light started racing outward in all directions. Our view is limited to the part of that light that has finally intersected with our position in space. Everything outside that sphere lies beyond our current horizon, but it's still part of the universe. If the universe is spatially infinite, then beyond the observable universe there would be an endless continuation of galaxies, clusters, and cosmic structures. If it's finite but unbounded, the continuation might loop back on itself, meaning that if you traveled far enough, you could theoretically end up back where you started without ever encountering a wall. Either way, there's no evidence of a hard boundary out there. What's more, the same laws of physics, the same types of matter, and the same cosmic structures we see nearby are likely mirrored beyond our view. We have good reason to believe this because the universe appears remarkably uniform on large scales. The distribution of galaxies and cosmic microwave background radiation is statistically the same in every direction we look. If there were a sudden end to space just beyond our horizon, we'd expect to see clues in the form of asymmetries or distortions in that data, and we don't. It's humbling to realize that what we call the universe in casual speech is really just the observable universe, a cosmic sample. We are peering through a narrow window into a much grander reality. Our telescopes give us a spectacular view, but the window has edges, and beyond them is a vastness we can only infer. The truth is, we don't know how far space goes. It could be so large that the observable portion is a vanishingly tiny fraction of the whole. It could contain regions so distant that they're causally disconnected from ours forever, meaning we can never exchange information, matter, or energy with them. For all practical purposes, they are separate universes, yet still part of the same overarching space-time fabric. This is why many cosmologists think of the observable universe as our cosmic neighborhood. It's the part we can explore, map, and understand through observation. But just as your neighborhood is not the whole planet, the observable universe is not the whole cosmos. Somewhere beyond the limits of our sight, the story of the universe continues, endlessly, perhaps, with galaxies forming, stars burning, planets orbiting, and who knows what else unfolding, utterly invisible to us. And that thought, that the real universe is vastly larger than the one we see, is as humbling as it is exhilarating. It means that no matter how advanced we become, there will always be more beyond our reach, more to imagine, more to wonder about. The cosmic stage doesn't end at the edge of the spotlight. It stretches into a darkness so vast that we can only dream of what lies there. In the early 20th century, the universe was thought to be static and unchanging on the largest scales. Many astronomers believed that the stars and galaxies were arranged in a fixed, eternal cosmos. That idea began to crumble in 1929, when Edwin Hubble made a discovery that would completely transform our understanding of reality. Distant galaxies weren't just drifting around at random, they were all moving away from us. Hubble's evidence came from studying the light emitted by galaxies. When you pass white light through a prism, you get a spectrum of colors, and within that spectrum, certain chemical elements leave telltale absorption lines. In the laboratory, these lines appear at fixed wavelengths. But in the light from distant galaxies, astronomers found that the lines were shifted toward the red end of the spectrum, what we call a redshift. At first, this was puzzling. But the explanation came from the Doppler effect, the same principle that makes an ambulance siren sound lower in pitch as it moves away from you. For light, a shift toward red means the source is moving away. A shift toward blue means it's moving toward you. By measuring these red shifts, Hubble and his colleagues realized that nearly all galaxies were receding from us, and that their speed increased with distance. The farther away a galaxy was, the faster it seemed to be moving. This relationship became known as Hubble's law, and it revealed something profound: the universe itself is expanding. Space is not a static stage where galaxies drift around like actors. Instead, the stage itself is stretching, and the galaxies are like dots on a balloon that's being inflated. As the balloon grows, the dots move farther apart, not because they're traveling across the balloon's surface, but because the surface itself is expanding. This expansion is uniform on large scales, meaning it doesn't have a special center. From any galaxy's perspective, all the others appear to be moving away. If you lived in a galaxy billions of light-years from here, you would still see the same pattern. The farther away something is, the faster it's receding. Hubble's discovery fit beautifully with the predictions of Einstein's general theory of relativity, a theory Einstein himself had initially resisted applying to the whole universe. In fact, Einstein had once inserted a cosmological constant into his equations to force a static solution, something he later called his biggest blunder, after Hubble's work showed the universe was expanding naturally. The idea that space itself stretches is key. Galaxies aren't racing through some pre-existing void. Instead, the fabric of space-time between them is increasing. On smaller scales, such as within galaxies or clusters of galaxies, gravity holds matter together against expansion. But on cosmic scales, the stretching dominates. This expansion is why the observable universe is so much larger than you'd expect from its age alone. Light from distant galaxies began its journey when they were far closer to us, but as it traveled, space expanded, carrying them farther away. By the time the light arrived, those galaxies were tens of billions of light-years away in today's terms. Hubble's simple but revolutionary observation, that the cosmos is expanding, reshaped cosmology. It turned the universe from a static, eternal backdrop into a dynamic, evolving entity with a history and, potentially, a future destiny. It also opened the door to the idea of a beginning, leading directly to the modern Big Bang theory. One of the most counterintuitive consequences of an expanding universe is that there are regions of space moving away from us faster than the speed of light. At first glance, this sounds impossible. After all, isn't the speed of light supposed to be the ultimate cosmic speed limit? But the trick is in understanding what is moving. Einstein's special relativity sets the speed of light as the maximum speed that objects can travel through space. Nothing with mass can accelerate through space to outrun a photon. But the expansion of the universe is not about things moving through space, it's about space itself stretching. And that stretching can happen at any rate. Even one that carries galaxies apart faster than light could cover the distance between them. Imagine you're standing on a rubber sheet with a friend 10 meters away. You toss a marble toward them, rolling it across the sheet. If the sheet is still, the marble reaches them just fine. But if you start stretching the sheet fast enough, the distance grows quicker than the marble can travel, and it never reaches your friend. The marble hasn't broken any speed laws, it's just being outpaced by the stretching of the surface. In cosmology, light plays the role of the marble, and space itself is the rubber sheet. Now, because of this, there's a kind of cosmic point of no return. Any galaxy far enough away will be receding from us faster than the speed of light due to the expansion of space. That means no matter how long we wait, light it emits today will never arrive here. These regions are beyond what's called our cosmic event horizon. We may still see some of them today, but only because the light we're seeing left them billions of years ago when they were closer and the expansion rate between us was slower. Over time, more and more galaxies will cross this threshold, moving into the forever unreachable zone. This isn't because they're speeding up in the sense of a rocket engine firing. It's because dark energy, the mysterious force causing the universe's expansion to accelerate, is steadily increasing the rate at which space stretches. This is one of the strangest aspects of our cosmic situation. Even as our telescopes grow more powerful, the universe itself is hiding things from us permanently. We live in a cosmos where there are galaxies out there right now, perhaps unimaginably beautiful, rich in stars and planets, whose light will never touch our detectors. They are moving away faster than light because the very space-time between us is expanding too quickly. In fact, this means that our observable universe is shrinking in a certain sense. Today, we can still see the afterglow of some extremely distant galaxies because we're catching ancient light that began its journey billions of years ago. But as time goes on, the light from those galaxies will be stretched to such faint, long wavelengths that it will fade from detectability. Eventually, they will vanish entirely from our skies, leaving behind a more and more empty-looking universe. This isn't just an abstract thought experiment. It has consequences for the ultimate fate of the cosmos and our place in it. In the far future, when only the galaxies in our local group remain visible, the evidence for an expanding universe will be hidden from any future observers who weren't around to record it now. They might look out into the darkness and assume, incorrectly, that the universe is static and empty beyond their small galactic neighborhood. So when we say that some regions of space are receding faster than light, we're really saying they've slipped permanently beyond our reach, not just for exploration, but even for observation. They are lost to us in the ever-growing gulf of space-time, hidden behind a boundary that no amount of technology can ever cross. When people first hear the phrase edge of the universe, it's tempting to imagine something tangible out there, maybe a colossal barrier, a shimmering energy field, or a kind of cosmic wall marking the end of space itself. Science fiction loves this imagery. The starship reaches the end of the map, the crew steps out to touch some glowing boundary, and beyond lies nothingness or another realm. But in reality, there is no cosmic fence, no brick wall, no glass dome over the universe. The edge that astronomers talk about isn't a structure you could bump into, nor a surface you could ever see up close. It's not a place in space at all. It's a limit defined by light, time, and the expansion of space-time. Think about being at sea, standing on the deck of a ship. In every direction, the water stretches to a distant line where it meets the sky, your horizon. It looks like the world ends there, but of course it doesn't. If you sailed toward that horizon, it would recede ahead of you, revealing more ocean beyond. There's no line in the water marking this is the end, just the limit of what you can see from where you stand. The universe works in a similar way. The edge of the observable universe is like that horizon. It's the farthest point from which light has had time to reach us since the Big Bang. If you could somehow travel toward that edge, you wouldn't find a wall. Instead, as you moved forward, your horizon would shift, revealing new regions of space that were previously hidden while other regions behind you faded beyond view. This is important because it flips the whole idea of an edge upside down. In normal life, edges are fixed. The edge of a cliff stays where it is, whether you walk toward it or away from it. The cosmic horizon isn't like that. It's relative to your position and bound to the laws of physics. Every observer in the universe, no matter where they are, has their own personal cosmic horizon, centered on them. That's also why it's misleading to think of us as being at the center of the universe just because the observable universe looks like a sphere around Earth. We are at the center of our observable bubble because we're seeing light that has traveled to us. A galaxy billions of light-years away is also at the center of its observable bubble, and from its perspective, we are out near its edge. And here's another twist. There are galaxies we can see right now, because their ancient light has finally reached us, that are actually already beyond the point of no return. The expansion of space has carried them so far away that any light they emit today will never reach us. They're visible now only because we're looking at the light they sent long ago, when they were closer. So the edge is not a structure in space. It's an effect of the universe's history. It's a moving, shifting horizon determined by how far light has traveled in an expanding space-time. The deeper truth is that the universe may not have any edge at all. Space might continue forever beyond what we can see, or it might loop back on itself without any boundary. Either way, there's no cosmic wall waiting for us out there, no fence to lean on and look over. In that sense, The universe is both infinite in its mystery and intimate in its relativity. The edge we talk about is a horizon in the truest sense, a limit of perception, not a physical barrier. And like a horizon at sea, it is both real and unreachable. Real because it defines what we can see, unreachable because it exists only in relation to where we stand in space and time. One of the most astonishing possibilities in cosmology is that the universe might be infinite. Not just unimaginably large, not just bigger than our observable bubble, but literally endless in all directions, stretching on without boundary, without edge, without a final last star marking where it all stops. If that's true, then the 92 billion light-year span of our observable universe is like the tiniest illuminated patch on an infinite canvas. It would be the equivalent of looking at a small circle of light cast by a lantern in a vast, unending forest. The forest doesn't stop where the light fades, it just keeps going into the dark. The only difference is that in space, the darkness isn't empty. It's filled with more galaxies, more stars, more matter and energy, and possibly more of the same patterns we see nearby. The idea of an infinite universe comes from several lines of evidence. First, when astronomers measure the large-scale geometry of the cosmos using the cosmic microwave background, the afterglow of the Big Bang, they find that space is flat to an incredible degree of precision. In cosmology, flat doesn't mean two-dimensional. It means that on large scales, the geometry of space follows the rules of Euclidean geometry, the kind you learned in school. Parallel lines never meet, and the angles of a triangle add up to 180 degrees. In a flat universe, space could be infinite in extent. Of course, flat geometry doesn't prove infinity. It's possible for the universe to be very large but finite, just like the surface of a balloon seems flat when you look at a tiny patch of it. But the measurements so far suggest that if the universe is finite, its size is so enormous that the observable part is just a microscopic fraction of the whole. If the universe truly is infinite, then something strange follows. The patterns of matter in it, galaxies, clusters, and empty voids, would repeat endlessly. Not in an obvious way, like a wallpaper pattern, but statistically. There would be infinite room for every possible configuration of matter to occur somewhere. That means somewhere out there, so far away that light could never reach us, there could be another region of the universe that looks almost exactly like our own observable bubble, with galaxies arranged in the same way, maybe even with a planet that's a near twin to Earth, orbiting a sun-like star, with someone like you sitting and wondering about the universe's edge. This isn't science fiction. It's just a natural consequence of an infinite space filled with matter obeying the same laws of physics everywhere. In an infinite universe, everything that is physically possible happens somewhere. Not once, but infinitely many times. The idea is thrilling, but it's also humbling. Because if the universe is infinite, then there is no edge to reach, no final destination where the universe stops and something else begins. You could travel forever in any direction and never come to a boundary. The only limits would be set by physics, your speed, your lifespan, and the expansion of space itself. This also changes how we think about our place in the cosmos. In a finite universe, you might be tempted to think of yourself as being inside something with a definable hole, a container, however large. In an infinite universe, there is no container. You're simply part of an endless fabric, woven into the structure of space and time that has no outer border. It's worth noting that infinity in physics is tricky. Some scientists are cautious about claiming the universe is infinite because infinity is a hard concept to test. We can only measure what's inside our observable bubble. If the universe is larger than that, but not infinite, we might not ever know the difference. For all we can tell right now, the observable universe could be just one tile in a cosmic floor that extends forever. Whether it's infinite or just inconceivably vast, the lesson is the same. There's no physical wall, no edge, no last frontier in space. The universe doesn't end. It simply extends beyond our sight, possibly without limit. The possibility that the universe could be finite but unbounded is one of those concepts that feels like a riddle until it clicks, and when it does, it completely changes how you imagine reality. The best way to picture it is through the balloon analogy, which cosmologists love because it neatly sidesteps the misleading mental image of an edge. Imagine a balloon. Now, imagine you are an ant walking on the surface of that balloon. You're two-dimensional in this analogy. You can move left, right, forward, or backward along the balloon's surface, but you can't burrow inside it or float above it. As you start walking in a straight line, you never run into a wall or a cliff. You just keep going, and eventually, if you walk long enough, you'll end up back where you started. The key detail here is that the balloon's surface is finite. It has a measurable area, but it has no edges. There's no point on the balloon where you can say, this is the end of the surface. Instead, the surface curves back on itself. You can travel forever without encountering an edge, yet you're moving within a closed shape. Now, replace the two-dimensional balloon surface with three-dimensional space. If our universe is finite but unbounded, it means that space is curved in such a way that if you could travel in a straight line long enough, you'd eventually loop back to your starting point, just like the ant on the balloon. The difference is that instead of a two-dimensional curve into a third dimension, space itself would be curved in a higher dimensional way that's hard to picture. But mathematically, it works. This idea goes back to Einstein's general theory of relativity, which showed that mass and energy can bend space-time. If the overall density of matter and energy in the universe is above a certain threshold, space could curve back on itself into a kind of higher dimensional sphere, called a three-sphere. In such a universe, there's no boundary, but the total volume is finite. From inside, you wouldn't notice any obvious curvature on small scales, just as the ant thinks the balloon's surface looks flat in its immediate neighborhood. But on the largest scales, the shape of the universe would subtly determine the paths that light and matter can take. A finite but unbounded universe also challenges our instinctive picture of beyond. On the balloon, there's an inside and an outside in the real three-dimensional world, but those don't exist for the ant. For the ant, the balloon's surface is all of reality. Similarly, if our universe curves back on itself in higher dimensions, there's no outside in any physical sense. Space doesn't need an outer container, it's self-contained. This model also neatly removes the need for a literal edge. You never run into a cosmic wall, because there isn't one. Every point in space is equivalent. You can keep moving forever without finding the end, and yet the total volume is finite. It's like living in a giant cosmic video game with a wraparound map. Walk far enough in one direction, and you reappear where you started. Observations so far suggest that if the universe is finite and curved, its size must be much larger than the observable universe, because we don't see repeated patterns in the cosmic microwave background that would indicate we're seeing the same regions of space from different angles. But the possibility is still open, and if it's true, the shape of the universe would be one of the most profound facts about reality we could ever discover. It's a deeply mind-bending scenario, a universe that is both limited and limitless, both closed and endless in travel, a place where you can journey forever without ever reaching an edge because space itself folds back upon itself in ways our everyday intuition can barely grasp. When cosmologists talk about the shape of the universe, they don't mean whether it's shaped like a ball, a cube, or a giant donut floating in some external space. They're talking about its geometry, the way space is curved, or not, on the largest possible scales. This is a question with surprisingly concrete answers, thanks to Einstein's general theory of relativity, which tells us that the overall geometry of the cosmos depends on its total mass-energy content. There are three main possibilities: flat, closed, and open. A flat universe is one in which space follows the rules of Euclidean geometry, the same kind you learned in school. Parallel lines stay parallel forever. The sum of the angles in a triangle is exactly 180 degrees, and very large circles have circumferences that match the formula C equals 2r without any weird corrections. In such a universe, space could be infinite, stretching forever in all directions, or it could be finite but wrapped around in a way that's difficult to visualize, like the finite but unbounded scenario we discussed earlier. A closed universe is one with positive curvature, like the surface of a sphere. On a large enough scale, parallel lines eventually meet, and the angles of a triangle add up to more than 180 degrees. A closed universe is finite in size, and if you travel far enough in one direction, you eventually loop back to where you started. This is the balloon analogy in action, except in 3 spatial dimensions instead of 2. An open universe is one with negative curvature, like the surface of a saddle. Parallel lines diverge, and triangles have angle sums of less than 180 degrees. In an open universe, space is infinite, but it curves outward, making its geometry distinctly different from the flat case. So, which one do we live in? To find out, scientists have used extremely precise measurements of the cosmic microwave background, CMB, the afterglow of the Big Bang, collected by missions like NASA's WMAP, Wilkinson Microwave Anisotropy Probe, and SR's Planck satellite. The CMB contains tiny fluctuations in temperature that serve as a cosmic ruler, allowing astronomers to measure how light has traveled across the universe and detect any large-scale curvature. The results? All the data so far suggest that our universe is remarkably flat, to within a fraction of a percent. This doesn't prove it's infinite, but it means that if there is curvature, the radius of that curvature is so huge that it's far beyond the reach of our observable bubble. Flatness also fits neatly with the inflationary model of the early universe, which predicts that the rapid exponential expansion right after the Big Bang would have stretched any initial curvature to near zero, just as inflating a balloon makes a small patch look flatter and flatter the more it expands. That said, flat in cosmology doesn't mean boring or featureless. Our universe is still dynamic, expanding, and full of complex structures like galaxies, clusters, and cosmic filaments. But on the very largest scales, its geometry seems to follow the simple, familiar rules of a flat space, a finding that's as elegant as it is mysterious. Because if the universe truly is perfectly flat, that raises another question: why? And is it just an observational coincidence, or is it a deep clue to the very nature of reality? When we talk about the edge of the universe in astronomy, we are not describing a physical boundary, fence, or cliff in space. Instead, we're talking about something much more abstract, the limit of what we can observe, given the constraints of physics and the history of the cosmos. That limit exists because of one simple fact: light takes time to travel. The universe has only existed for about 13.8 billion years, so the farthest we can possibly see is the distance light has been able to travel in that time. This is what defines our observable universe. Everything beyond that remains hidden from us, not because it doesn't exist, but because its light hasn't had enough time to get here yet. This is an important distinction. The observable universe is a sphere centered on us, but it is not the universe. It's just the part of the cosmos that has been able to communicate with us since the Big Bang. If you were on a galaxy 10 billion light-years away, your observable universe would be centered there, overlapping ours in some places but also containing regions we can't see at all. It's tempting to picture the edge of this observable sphere as the edge of all reality. But that's like standing on a foggy mountaintop and assuming the world ends where the fog starts. The fog in this analogy is the limit of light that's had time to reach you. You can't see what's beyond it, but you can be almost certain there's more landscape out there. In fact, in cosmology, the limits of observation are always moving. As time passes, light from more distant regions has time to arrive, so our observable sphere grows larger. But this growth has a catch, because the universe is expanding, and that expansion is accelerating due to dark energy. There are regions that will always remain forever beyond our observational reach. They are receding from us faster than light, a consequence of space itself expanding, not because they're breaking the cosmic speed limit, so no matter how much time passes, their light will never catch up. What this means is that the edge we see is personal and temporary. It's personal because every observer in the universe has their own observable sphere, centered on them. It's temporary because the boundary changes over cosmic time, but only for some regions. Others slip permanently over the horizon, like ships vanishing beyond the curvature of the Earth, never to be seen again. So when scientists say the edge of the universe, what they usually mean is the edge of the observable universe. It's not the same as the universe's physical extent, which might be much larger or even infinite. The real universe might stretch far beyond what we can see, containing countless more galaxies, stars, planets, and maybe even entirely different regions with different cosmic histories. The beauty of this perspective is that it reminds us how limited our cosmic window really is. We are peering through a keyhole into an unfathomably vast room, and the keyhole is determined by the speed of light, the age of the universe, and the geometry of space-time. It's a humbling boundary, not because it marks the end of reality, but because it reminds us how much is hidden from view. When we look out into space, we're also looking back in time. This isn't a poetic metaphor, it's a literal consequence of the fact that light travels at a finite speed. Every distant galaxy we see is shown to us as it was when the light left it, not as it is right now. The farther away something is, the longer that light has been traveling, and the older the snapshot we're receiving. The ultimate limit to this cosmic time-traveling gaze is the cosmic microwave background, CMB. This faint glow is the oldest light we can detect, and it comes from a time about 380,000 years after the Big Bang, unimaginably close to the beginning of the universe when compared to its current age of 13.8 billion years. Before that moment, the cosmos was hidden behind a glowing, impenetrable veil. Why that specific point in time? Early in the universe's history, the cosmos was incredibly hot and dense, filled with a thick plasma of electrons, protons, and photons all bouncing off one another like an endless game of billiards. Photons, particles of light, couldn't travel freely. Every time they tried, they'd smash into an electron and scatter in a new direction. The universe was, in a sense, opaque, like the interior of a glowing star. Then, as the universe expanded, it cooled. Around 380,000 years after the Big Bang, it reached a temperature low enough, roughly 3,000 kelvins, for electrons and protons to combine into neutral hydrogen atoms. This event is called recombination. Suddenly, photons were free to travel without constant scattering. The universe became transparent for the first time. Those first freely traveling photons have been racing through space ever since, gradually stretched into the microwave part of the spectrum by the ongoing expansion of the universe. Today, we detect them as the CMB. When we observe the CMB, we are not seeing galaxies or stars. We're looking at a cosmic baby picture, the universe itself as it existed before any stars had formed. It's a smooth but subtly mottled glow, with tiny fluctuations in temperature that correspond to tiny variations in density. Those variations were the seeds from which all later cosmic structures, galaxies, clusters, and cosmic filaments, eventually grew. Seeing the CMB is like standing on the shore of an ancient ocean of light, knowing that on the other side is a time when the universe was something entirely different. We cannot see directly into that earlier era with light because photons simply didn't have the freedom to travel. The CMB forms a sort of light horizon for electromagnetic observations. Beyond it lies the universe's dark age, an era visible only to messengers other than light, like neutrinos or gravitational waves. Every time we gaze at this ancient radiation, we're peering across nearly the entire history of the cosmos, to the moment when space first became transparent and the journey of light truly began. That's why, for now, the CMB is the farthest back we can see, a wall not made of matter, but of time and physics itself. Before the release of the cosmic microwave background, the universe was in a radically different state, a hot, dense, seething ocean of particles and energy. Imagine the brightest, most blindingly hot fog you can conceive of, except instead of tiny droplets of water suspended in air, it was made of plasma, a chaotic soup of electrons, protons, and photons all colliding with each other in a relentless frenzy. In this early epoch, the universe was so hot that no atom could exist intact. The energy of the photons was high enough to knock electrons away from protons instantly, preventing the formation of neutral hydrogen. Without neutral atoms, light couldn't travel freely. Instead, photons constantly bounced off free electrons in a process known as Thomson scattering. You could say light was trapped inside the plasma, just as light is trapped inside the interior of our sun until it finally escapes from the surface. This state of affairs lasted for hundreds of thousands of years after the Big Bang. And because light couldn't move freely, there was nothing like a clear view of the universe from the outside. Any observer, if such an observer could exist, within that early cosmos would be completely engulfed by brightness. Not because the universe was filled with stars, it wasn't, but because everything everywhere was glowing with the intense heat of the primordial plasma. This is why, as far as electromagnetic observations go, we can't see further back than the CMB. The CMB marks the moment when the universe cooled enough for electrons and protons to combine into neutral hydrogen, when the fog lifted and light began its uninterrupted journey across space. Before that, photons simply didn't have the freedom to travel without scattering. It's worth noting that opaque here doesn't mean dark. Quite the opposite. The early universe was filled with light, but that light couldn't carry images or information about distant places. It was like staring into a solid wall of glowing metal. All you would see is the blinding glow itself, not the shapes or patterns of whatever lies beyond. So, before the CMB, the history of the universe is hidden to traditional telescopes. That doesn't mean it's unknowable, just that we need different tools to explore it. Theories like cosmic inflation make predictions about what the universe was like in those first fractions of a second, and alternative messengers, such as neutrinos or gravitational waves, could, in principle, let us probe those earlier times. In a sense, the universe before the CMB was a place without a visible sky as we understand it today. It was a churning, luminous fog, filled with energy but devoid of structures like galaxies or stars. Only after the release of the CMB did the cosmic stage become transparent enough for the great play of structure formation to begin, leading, billions of years later, to planets, life, and us, standing here, trying to imagine an era that light itself cannot show us. If light can't take us further back than the cosmic microwave background, then to peer deeper into the universe's history we need to find other messengers, signals that don't get blocked, scattered, or absorbed by that thick, hot plasma of the early cosmos. Two of the most promising candidates are neutrinos and gravitational waves. Neutrinos are sometimes called ghost particles because they almost never interact with matter. Trillions of them are streaming through your body right now, passing effortlessly through the Earth as though it were barely there. In the early universe, neutrinos were produced in enormous quantities within the first second after the Big Bang. Unlike photons, they barely interacted with the dense plasma, meaning they could escape freely while the universe was still opaque to light. These ancient neutrinos, known as the cosmic neutrino background, are thought to fill the cosmos to this day, carrying information from a time far earlier than the CMB, back to when the universe was less than 1 second old. The challenge? Detecting them is incredibly difficult. Neutrinos are famously elusive, and the ones from the early universe would have extremely low energies, making them even harder to catch than the neutrinos we detect from the Sun or supernovae. While we haven't yet directly observed this cosmic neutrino background, physicists are developing techniques and detectors that might one day let us measure it, opening a window to a chapter of cosmic history that has never been seen. Then there are gravitational waves, ripples in the fabric of space-time itself. First predicted by Albert Einstein in 1916 and directly detected a century later in 2015, gravitational waves are generated by massive accelerating objects, like colliding black holes or neutron stars. But they can also be generated by the most violent and fundamental processes in the early universe, such as cosmic inflation or phase transitions in the energy fields that govern the infant cosmos. Unlike light, gravitational waves are not blocked by matter or energy. They would have been able to pass straight through the hot, dense plasma that trapped photons, potentially giving us information from the universe's very first fractions of a second. Detecting such primordial gravitational waves would be like finding a fossilized echo of the Big Bang itself. In theory, these gravitational waves could tell us about events that happened at unimaginably high energies, far beyond what any human-made particle accelerator could reproduce. Observing them would not only illuminate the pre-CMB universe, it could also test fundamental theories about the origin of space-time, the nature of quantum gravity, and whether our universe is part of a much larger multiverse. Right now, our gravitational wave observatories, like LIGO and Virgo, are tuned to catch waves from astrophysical events, not the ultra-long wavelength ripples from the Big Bang. But future detectors, such as space-based interferometers like LISA, or experiments that measure the polarization patterns in the CMB itself, might be able to detect these primordial signals. In essence, neutrinos and gravitational waves are like ancient messengers who left long before light could escape, carrying secrets from a hidden era. If we can learn to listen to them, we'll extend our cosmic timeline not just to 380,000 years after the Big Bang, but potentially to the first heartbeat of the universe itself. The cosmic inflation theory is one of the most mind-bending and transformative ideas in modern cosmology. It suggests that in the tiniest fraction of a second after the Big Bang, we're talking less than a trillionth of a trillionth of a trillionth of a second, the universe underwent an almost inconceivably rapid expansion. This wasn't the steady kind of expansion we see today, where galaxies gradually move away from each other. Inflation was an exponential growth of space itself. In this brief moment, the size of the universe is thought to have increased by a factor so enormous it's almost beyond comprehension, something like 10 times in volume. That's like taking a subatomic particle and stretching it to the size of the observable universe in the blink of an eye. Why propose such an outrageous idea? It turns out inflation neatly solves several puzzles that the original Big Bang model couldn't fully explain. One of these is the horizon problem. When we look at the cosmic microwave background, we see that it's astonishingly uniform in temperature across the sky. That's odd, because different regions of the CMB are so far apart that, under normal expansion, Light couldn't have traveled between them to even out their temperatures. Inflation solves this by suggesting that all those regions were once much closer together, close enough to exchange energy and reach the same temperature, before being blown apart by inflation. Then there's the flatness problem. The geometry of the universe today is extremely close to flat, meaning parallel lines stay parallel and the rules of Euclidean geometry still apply on the largest scales. Without inflation, the conditions for such flatness would have to be absurdly fine-tuned in the early universe. Inflation naturally drives the curvature of space toward flatness, much like blowing up a balloon makes a small patch of its surface look flatter. Inflation also helps explain why we don't see certain hypothetical relics of the early universe, such as magnetic monopoles, which are predicted by some grand unified theories of particle physics. The rapid expansion would have diluted these particles to near non-existence in our observable region. But perhaps one of the most fascinating aspects of inflation is that it predicts the tiny quantum fluctuations in the early universe would get stretched to cosmic scales. These fluctuations became the seeds for all large-scale structure we see today. Galaxies, clusters, superclusters, all grew from minuscule quantum jitters, magnified by inflation into density variations across the cosmos. This is why the faint temperature variations in the CMB are considered smoking gun evidence for inflation. They match the statistical patterns predicted by the theory. The mechanism behind inflation is thought to involve a special field, often called the inflaton field, whose energy caused space to expand at an accelerating rate. When inflation ended, the energy of this field was released, reheating the universe and creating the hot, dense conditions we associate with the standard Big Bang model. Inflation, if correct, radically changes our understanding of the beginning of the universe. It suggests that what we think of as the Big Bang wasn't the start of everything, but rather the end of inflation's explosive expansion phase and the start of a slower, more familiar cosmic evolution. And it also leaves the door wide open to even wilder possibilities, like the idea that inflation might never completely stop everywhere, giving rise to an endless multiverse of bubble universes, each potentially with its own laws of physics. In short, cosmic inflation takes the already staggering scale of the universe and turns the dial up to a level where words barely do justice. It's not just that the universe is big, it's that in its first instant, it grew faster than our intuition can even process, setting the stage for everything that would ever exist. The multiverse hypothesis takes the already awe-inspiring concept of the universe and pushes it into even stranger territory. Instead of there being just one universe, the one we see and live in, this idea proposes that our universe could be just a single bubble in an enormous, perhaps infinite, cosmic foam. The roots of this idea often come directly from cosmic inflation theory. Certain versions of inflation, especially eternal inflation, suggest that while inflation ended in our region of space, it may still be going on elsewhere. Imagine a vast cosmic field in which regions randomly stop inflating, forming individual bubble universes, while the rest continues to expand. Each bubble could have its own laws of physics, constants of nature, and even numbers of dimensions. Our observable universe would simply be the inside of one such bubble. In this picture, the space outside our bubble isn't empty nothingness. It's more like a seething, ever-expanding landscape where new universes are continually being born. And because these bubbles are separated by regions of space still undergoing inflation, they can never interact in any meaningful way. The distance between them grows faster than light can travel, so each bubble remains forever isolated. There are also other pathways to a multiverse besides inflation. For example, quantum mechanics, particularly in the many worlds interpretation, suggests that every quantum event spawns multiple realities, each containing a different outcome. In this view, the multiverse isn't just spatial but also a constantly branching tree of histories. String theory introduces yet another kind of multiverse, sometimes called the landscape multiverse. String theory allows for a huge variety of possible vacuum states, potentially 10 to the power of 500 different configurations, each corresponding to a universe with different laws of physics. The multiverse would then be a vast collection of all these possibilities. While the multiverse is a tantalizing concept, it's important to note that it's still highly speculative. There's no direct observational evidence for other universes, and some physicists argue that if we can never interact with or measure them, the idea might lie outside the realm of traditional science. Others counter that indirect evidence, like the fine-tuning of physical constants or certain patterns in the cosmic microwave background, could hint at a multiverse, even if we can never visit it. From a philosophical perspective, the multiverse challenges our already fragile sense of cosmic centrality. Copernicus taught us we're not at the center of the solar system. Modern astronomy taught us we're not at the center of the galaxy. Cosmology taught us we're not at the center of the universe. The multiverse takes this one step further. Perhaps our entire universe is not special, but simply one small patch in a vast and varied cosmic archipelago. It's a dizzying idea, one that makes the edge of the universe even harder to define. If the multiverse is real, then the edge of our universe might be just the thin, expanding wall of our bubble, beyond which lies not emptiness, but the unimaginable diversity of other universes. Whether we can ever prove it or not, the multiverse reminds us that the cosmos might be far richer and stranger than even our boldest scientific guesses. The edge of the observable universe isn't a fixed, permanent boundary, it's constantly shifting. This is because light, from more and more distant regions of space, is continuously arriving, expanding our visible horizon as time passes. Imagine the universe as a vast ocean and us as sailors in a small boat. As we sit there, light waves, our messengers from the distant cosmos, keep reaching us from farther shores. The longer we wait, the more of the ocean we can glimpse. Right now, the most distant light we can see has been traveling for 13.8 billion years. But because the universe has been expanding all that time, the sources of that light are now about 46 billion light-years away. Every passing second, light from even more distant galaxies is completing its journey to Earth. This means that in the future, astronomers will be able to see objects that are currently just beyond our reach. It's as if our cosmic photograph is slowly gaining new pixels at the edges. This is called the particle horizon, the growing sphere around us containing everything whose light has had time to arrive since the Big Bang. But here's where things get tricky. Even though our observable universe is expanding in terms of what we can see, there's another limit called the cosmic event horizon. This is the boundary beyond which events will never be able to affect us, no matter how long we wait. Because the universe's expansion is accelerating, driven by dark energy, there are regions of space receding from us faster than the speed of light. Any light they emit now will never catch up to us. These galaxies are like ships sailing away across an ever-widening gulf, permanently out of communication range. So, over cosmic time, two things happen at once. Our observable horizon grows, revealing objects that were once hidden beyond our sight. But more and more galaxies slip beyond the event horizon, disappearing from our future view forever. This creates a bittersweet picture of the universe. On one hand, the cosmic storybook slowly reveals earlier and earlier chapters as new light arrives. On the other hand, entire regions of the cosmos are leaving our story entirely, pulled away by the relentless expansion of space. In fact, in the extremely far future, trillions of years from now, the only galaxies still visible will be our own gravitationally bound group, everything else having faded beyond the cosmic event horizon. In essence, the edge of what we can see is a moving target, defined not by a physical wall but by the relentless race between the speed of light and the speed of cosmic expansion. It's an edge that invites hope, because it grows, and humility, because no matter how powerful our telescopes become, there will always be places forever out of reach. The heat death and the concept of event horizons take the story of the universe to its far, distant future, a time so remote that it makes even the age of the dinosaurs look like the blink of an eye. These ideas aren't about what's happening at the edge of the universe now, but about what the edge will look like when the cosmos has aged beyond anything we can imagine. Let's start with the event horizon in a cosmological sense. Just like a black hole has an event horizon, a boundary beyond which nothing, not even light, can escape, our universe has its own type of horizon caused by the accelerating expansion of space. Any galaxy beyond this horizon is receding from us faster than light due to the stretching of space itself. Light it emits now will never reach us, no matter how long we wait. This expansion is driven by dark energy, a mysterious force that makes up roughly 70% of the energy content of the universe. As dark energy continues to dominate, it causes the expansion rate to accelerate. Over billions and trillions of years, this means more and more galaxies will cross this cosmic event horizon, disappearing from view forever. They won't vanish instantly. Instead, their light will be stretched into longer and longer wavelengths, fading into the infrared, then into radio waves, until eventually they are completely undetectable. This leads us to the concept of heat death, which is a possible ultimate fate of the universe. In this scenario, the universe continues expanding forever, but in doing so, it becomes increasingly empty, cold, and dark. The term heat death can be misleading because it doesn't mean the universe burns up, quite the opposite. It refers to the thermodynamic idea of maximum entropy, the point at which all energy is evenly spread out and no useful work can be done. Over inconceivably long timescales, star formation will cease as galaxies run out of the cold gas needed to create new stars. Existing stars will burn out, leaving only remnants like white dwarfs, neutron stars, and black holes. Even those black holes, over an unimaginable span of time, will evaporate via Hawking radiation, leaving only a thin soup of low-energy photons and particles scattered across an ever-expanding void. From the perspective of a far-future observer, if such observers could still exist, the universe would be a lonely place. All but the nearest gravitationally bound galaxies would have faded beyond the cosmic event horizon. There would be no sign that other galaxies ever existed, no clue of the grand cosmic web we see today. The night sky would be almost entirely empty, perhaps with just a handful of dim stars in the local group. This future is sobering. It reminds us that the universe we see today, full of brilliant galaxies, glowing nebulae, and vibrant star clusters, is temporary. We just happen to live at a special moment in cosmic history when the night sky is rich with other galaxies, and the light from billions of years ago is still arriving at our doorstep. The heat death scenario may sound bleak, but it's also profoundly humbling. It emphasizes that we are living in a fleeting, golden age of cosmic visibility. Right now, the universe is open to us in a way it will never be again, a brief window when the great expanse is still filled with light and stories from the farthest corners of space. In the distant future, the cosmic stage will go dark, not with a bang, but with a slow, quiet fading into infinite stillness. When people first hear that the universe might not have an edge in the traditional sense, the next instinctive question is almost always, okay, but what's outside it? At first glance, that feels like a perfectly reasonable thing to ask. After all, almost everything in our day-to-day experience exists inside something else. A room is inside a house. A house is inside a city. A city is inside a country, which is inside a planet, which is inside space. It's natural for the mind to want to keep nesting things, like Russian dolls, and imagine that our universe must also be sitting inside some larger container. But here's the strange twist. That intuition doesn't work for the universe. Physicists often compare this to asking, what's north of the North Pole? It sounds like a logical question, but when you think about it, the concept breaks down. The North Pole is the northernmost point on Earth. If you travel in any direction from there, you're heading south. North doesn't exist beyond that point, not because there's a wall or a barrier, but because north is a direction defined within the surface of the Earth, and the surface simply doesn't extend that way. Similarly, the universe isn't something that sits in space. Space and time are part of the universe itself. Asking what's outside space is like asking what's beyond the surface of the Earth if you remove the surface. The idea doesn't even make sense in the same geometric or physical framework. In our best models of cosmology, the universe includes all of space, all of time, and all the matter and energy that exist. If there is an outside, it would require physics that goes beyond what we currently understand, and it might not even involve space or time as we know them. Of course, theories like the multiverse, which we discussed earlier, do entertain the idea of our universe being one of many. In those scenarios, outside could mean another bubble universe separated from ours by an inflating space we can't cross. But even then, we're not talking about an outside you could fly to in a spaceship. You can't just take a cosmic road trip to the next universe over. The expansion of space between bubbles is too fast, and the physics of that realm might be completely incompatible with ours. There's another subtle misconception here. People sometimes picture the universe as a giant sphere of galaxies surrounded by blackness, like a snow globe floating in empty space. But that image comes from looking at it from inside. From our point of view, the universe does appear like a sphere, the observable universe, because we can only see in all directions as far as light has traveled since the Big Bang. That's not the shape of the whole universe, though. It's just the shape of our personal field of view. Beyond that, the universe may continue without bound, or it may loop back on itself in ways we can't directly perceive. In short, Outside the universe might not exist in any meaningful way. The universe could be all there is, not because something is blocking us, but because the framework of inside and outside simply doesn't apply at the largest possible scale. It's a concept that forces us to stretch our thinking, abandon some of our most basic intuitions, and accept that reality might not map neatly onto our everyday experience. Dark energy is one of the most mysterious players in the entire cosmic story, and it's directly responsible for shaping what we call the edge of the universe. Without it, the expansion of the cosmos might have slowed down under the pull of gravity, perhaps even reversed into a big crunch. Instead, something entirely unexpected happened. The universe's expansion began speeding up, pushing distant galaxies away from us faster and faster. The discovery came in the late 1990s, when two separate teams of astronomers were studying distant Type Ia supernovae, exploding stars that act like standard candles because they all shine with roughly the same intrinsic brightness. By comparing how bright these explosions appeared from Earth, astronomers could determine their distances. When they plotted these distances against the redshift of the galaxies they were in, a measure of how much their light had been stretched by cosmic expansion, the results were shocking. The galaxies weren't just moving away, they were accelerating in their retreat. This was completely opposite to what most scientists expected. Gravity, being attractive, should have been slowing the expansion down over time, not speeding it up. To explain this, researchers proposed the existence of a new form of energy, dark energy, that exerts a repulsive gravitational effect. Unlike matter, which clumps together and pulls things inward, dark energy appears to be uniformly spread throughout space and causes space itself to expand more rapidly. One simple explanation is to treat dark energy as a cosmological constant, first introduced, and later abandoned, by Einstein. In this model, dark energy's density stays the same as the universe expands, meaning that its influence grows over time relative to matter. Billions of years ago, matter and radiation dominated. Second, the energy requirements are astronomical. Accelerating just 1 kilogram to 99.99% of light speed would require more energy than humanity currently produces in decades, maybe centuries. And that's ignoring the fact you'd have to slow down at the other end, requiring the same enormous energy again. But here's the deeper challenge. The edge you'd be chasing isn't just far away. In many cases, it's receding faster than light because of the expansion of the universe. This is allowed by relativity because it's not the galaxies themselves moving through space faster than light, it's space itself stretching between you and them. That means there are regions of the universe that are not just currently unreachable, but forever unreachable, even if you traveled at light speed for the rest of time. So what about the parts of the universe that are technically reachable? Even those are daunting. At our current best propulsion technology speeds, which are tiny fractions of light speed, it would take tens of thousands of years just to reach the nearest star, Proxima Centauri, which is 4.24 light-years away. Now multiply that by billions for the scale of the observable universe, and you see why the idea collapses under its own enormity. Even in theoretical scenarios with near-light speed travel, you'd face another problem: cosmic radiation and collisions with even tiny bits of matter in space. At those speeds, a grain of dust would hit with the force of an explosive. Shielding against that would require an impractical amount of mass and engineering. The bottom line is that visiting the edge of the universe is not like taking a really long trip, it's like trying to run to the end of a mirage. The boundary we see is a product of light travel time and expansion, and it will always recede faster than we can chase it. From a practical standpoint, the energy and time required to even get close are effectively infinite. The only way we can explore that edge is the way we already do, by catching the light, gravitational waves, and other signals that have been traveling toward us since the dawn of time, letting them tell the story of the farthest places we will never visit. Science fiction has always had a fascination with the edge of the universe. Across books, movies, and television, storytellers often picture it as a literal frontier, a tangible place where the fabric of reality ends, waiting for brave explorers to pierce its veil. Sometimes it's depicted as a glowing wall of energy, other times as an infinite waterfall of stars pouring into nothingness, or even as a curtain that, once passed through, reveals another dimension entirely. These artistic interpretations can be breathtaking, but they also reveal something about human psychology. We're wired to imagine boundaries as solid, visible, and crossable. In countless sci-fi narratives, the edge might be a shimmering barrier you can fly up to and touch. Think of Star Trek episodes where the Enterprise encounters the galactic barrier, an actual wall of energy surrounding the Milky Way. Or in The Truman Show, where the protagonist literally sails to the edge of his artificial world and finds a painted sky. These visuals are compelling because they give a sense of arrival. They suggest that exploration has a destination, a point where you can say, "We've made it." Other works of fiction have imagined the edge as a dangerous drop-off, the cosmic equivalent of sailing off the map in the age of exploration. In older speculative tales, a ship might cross into a region where stars fade, time behaves strangely, or space dissolves into chaos. In some stories, the edge is a gateway, leading to other universes or higher planes of existence. It's a natural storytelling device, an ultimate threshold for heroes to cross. But here's where reality laughs gently at our imagination, the actual cosmos. Second, the energy requirements are astronomical. Accelerating just 1 kilogram to 99.99% of light speed would require more energy than humanity currently produces in decades, maybe centuries. And that's ignoring the fact you'd have to slow down at the other end, requiring the same enormous energy again. But here's the deeper challenge. The edge you'd be chasing isn't just far away. In many cases, it's receding faster than light because of the expansion of the universe. This is allowed by relativity because it's not the galaxies themselves moving through space faster than light, it's space itself stretching between you and them. That means there are regions of the universe that are not just currently unreachable, but forever unreachable, even if you traveled at light speed for the rest of time. So what about the parts of the universe that are technically reachable? Even those are daunting. At our current best propulsion technology speeds, which are tiny fractions of light speed, it would take tens of thousands of years just to reach the nearest star, Proxima Centauri, which is 4.24 light-years away. Now multiply that by billions for the scale of the observable universe, and you see why the idea collapses under its own enormity. Even in theoretical scenarios with near-light speed travel, you'd face another problem: cosmic radiation and collisions with even tiny bits of matter in space. At those speeds, a grain of dust would hit with the force of an explosive. Shielding against that would require an impractical amount of mass and engineering. The bottom line is that visiting the edge of the universe is not like taking a really long trip, it's like trying to run to the end of a mirage. The boundary we see is a product of light travel time and expansion, and it will always recede faster than we can chase it. From a practical standpoint, the energy and time required to even get close are effectively infinite. The only way we can explore that edge is the way we already do, by catching the light, gravitational waves, and other signals that have been traveling toward us since the dawn of time, letting them tell the story of the farthest places we will never visit. Science fiction has always had a fascination with the edge of the universe. Across books, movies, and television, storytellers often picture it as a literal frontier, a tangible place where the fabric of reality ends, waiting for brave explorers to pierce its veil. Sometimes it's depicted as a glowing wall of energy, other times as an infinite waterfall of stars pouring into nothingness, or even as a curtain that, once passed through, reveals another dimension entirely. These artistic interpretations can be breathtaking, but they also reveal something about human psychology. We're wired to imagine boundaries as solid, visible, and crossable. In countless sci-fi narratives, the edge might be a shimmering barrier you can fly up to and touch. Think of Star Trek episodes where the Enterprise encounters the galactic barrier, an actual wall of energy surrounding the Milky Way. Or in The Truman Show, where the protagonist literally sails to the edge of his artificial world and finds a painted sky. These visuals are compelling because they give a sense of arrival. They suggest that exploration has a destination, a point where you can say, "We've made it." Other works of fiction have imagined the edge as a dangerous drop-off, the cosmic equivalent of sailing off the map in the age of exploration. In older speculative tales, a ship might cross into a region where stars fade, time behaves strangely, or space dissolves into chaos. In some stories, the edge is a gateway, leading to other universes or higher planes of existence. It's a natural storytelling device, an ultimate threshold for heroes to cross. But here's where reality laughs gently at our imagination. The actual cosmos offers no painted sky, no shimmering fence, no cosmic cliff face. If you could somehow reach the farthest point you can see, it wouldn't look special at all. It might be an ordinary galaxy, quietly forming stars and rotating in the dark. The edge is not a structure, but a condition, a limit defined by light and time. There's nothing to physically bump into, nothing that marks it as the end. It's more like a horizon at sea, a limit to your view, not a limit to what exists. And reality is, in many ways, far stranger than fiction. Instead of a fixed wall, the edge is constantly moving. Instead of an obstacle to break through, it's an uncatchable boundary, always receding due to cosmic expansion. The farther we try to look, the further back in time we peer, until we reach an era when galaxies didn't even exist, only a hot, dense plasma filling all of space. That's not the kind of edge you can touch. It's the kind you understand only through physics and mathematics. Interestingly, some modern science fiction has embraced this more nuanced vision. Stories like Interstellar and certain episodes of Doctor Who play with the idea of cosmic horizons, relativity, and unreachable regions of space, blending real astrophysics with speculative elements. The result is a kind of narrative honesty. The universe's actual rules are often more awe-inspiring than the fictional walls we use to imagine. Artistic interpretations might not match physical reality, but they serve a valuable role. They make abstract concepts emotionally tangible. A glowing boundary might be scientifically inaccurate, but it conveys the feeling of encountering something truly beyond comprehension. In that way, sci-fi doesn't just mislead, it inspires. Many astrophysicists grew up watching shows and reading stories that took liberties with the truth, and those visions planted the seeds for real-world curiosity. So while there is no cosmic curtain to pull back, the strange, shifting, and unreachable nature of the actual edge is arguably more profound than any fictional version. It's not a place to arrive at, it's a reminder of the vastness of reality and the limits of what any being, human or alien, can ever touch. In that sense, reality isn't less exciting than fiction. It's just playing a different game, one with rules that make the universe even more mysterious than the best special effects ever could. When we talk about the edge of the universe, we're not just having a scientific discussion. We're brushing up against some of the oldest and deepest philosophical questions humanity has ever asked. For millennia, thinkers, mystics, and mathematicians have wrestled with the idea of infinity, the nature of space, and the boundaries of reality. The modern astrophysical notion of the edge takes these ancient questions and puts them into a framework shaped by relativity, quantum theory, and cosmology. But the core mystery remains the same. If the universe has a limit, what lies beyond? And if it doesn't, what does infinity really mean? From a philosophical perspective, the edge isn't just a physical concept. It's a cognitive boundary, a place where our intuitions about how the world works begin to break down. In everyday life, boundaries are concrete: the end of a road, the rim of a cup, the walls of a room. These are finite, tangible limits. But the universe refuses to fit into this mental model. When scientists say there may be no edge at all, that space might extend infinitely or wrap back on itself, they're inviting us to think in ways that run counter to the instincts we've honed through everyday experience. There's also a profound temporal element here. The observable universe is bounded not by walls, but by time itself. We can't see beyond a certain distance because we can't see before the universe became transparent to light. In a way, the edge of the universe is also the edge of time as we can know it. This raises an almost poetic question. Is the past something that still exists somewhere out there, or is it gone forever? Einstein's relativity treats time as a dimension, woven together with space. From that perspective, the past, present, and future might all coexist in a four-dimensional block of reality. But for us, trapped in the flowing experience of time, the edge remains a frontier we can never cross. Thinking about the edge also forces us to confront the limits of human perception and knowledge. If there are parts of the universe we will never see, then there may be truths about reality that are forever inaccessible to us. This is not just a scientific limitation, but a philosophical one. Can we claim to truly understand the cosmos if vast regions of it are fundamentally unknowable? Some philosophers have drawn parallels to Plato's allegory of the cave. We are observers in a small bubble, seeing only the shadows that reach us, inferring a greater reality beyond. And then there's the ultimate ontological question. If there is no outside to the universe, what does that say about existence itself? The question, what's beyond the edge, might be meaningless in the same way that asking what's north of the North Pole is meaningless. It forces us to rethink space not as a container in which the universe sits, but as a property of the universe itself, something that may have no external reference point. For many, that's a deeply unsettling thought. For others, it's liberating, because it removes the need for a where or when in which the universe resides. Philosophically, the edge also speaks to the human condition. We are finite beings in a possibly infinite cosmos. We occupy one planet, in one galaxy, in one tiny observable patch of an incomprehensibly vast structure. And yet, here we are, aware of it. This awareness is, in itself, extraordinary. Carl Sagan often spoke about the cosmic perspective as both humbling and ennobling. Humbling because it reveals our smallness, ennobling because it shows our rare ability to contemplate the totality of existence. Finally, there's a philosophical beauty in the fact that the edge is always changing. As time passes, the boundary of what we can see shifts, allowing new light to reach us. This means the cosmos is not a static picture, but an evolving relationship between us and reality. The edge is not a destination, but an ever-moving horizon, reminding us that knowledge is a journey without a final stop. The more we think about the edge, the more we realize it's less about finding a literal boundary and more about confronting the boundaries of our own minds. In doing so, we discover that the greatest frontier might not be out there at all. It might be the expansion of our ability to imagine what out there means. Studying the so-called edge of the universe isn't just an exercise in cosmic daydreaming. It's one of the most powerful tools scientists have for uncovering the universe's deepest secrets. In astronomy and cosmology, looking outward is, in a very real sense, looking backward in time. Every photon that reaches our telescopes has been on a journey, sometimes for billions of years, carrying with it a story about the conditions of the universe at the moment it was emitted. By studying the most distant light we can detect, the faint signals from near the limits of the observable universe, we are effectively sifting through the cosmic record book. The edge of the observable universe serves as a natural laboratory for studying the early universe. This is because the farthest light we can see comes from the most ancient periods after the Big Bang. When we examine the faint galaxies near the observational limits, we're not seeing them as they are now, we're seeing them as they were billions of years ago, often in their infancy. These ancient objects reveal how galaxies first formed, how stars began to ignite, and how the first heavy elements were created. Without studying the edge, our knowledge of cosmic history would be hopelessly incomplete. One of the most important discoveries that came from looking to the edge is the cosmic microwave background, CMB. This faint glow, left over from about 380,000 years after the Big Bang, is the most ancient light we can directly observe. By mapping tiny fluctuations in the CMB, scientists have been able to determine the universe's age, composition, and even its overall geometry. This single piece of edge data has reshaped modern cosmology. Without it, we wouldn't know that the universe is 13.8 billion years old, or that dark matter and dark energy dominate its structure. Studying the edge also reveals the universe's rate of expansion. When Edwin Hubble discovered in the 1920s that galaxies are moving away from us, it was a groundbreaking moment. But it's by looking at the most distant galaxies that we've been able to refine that measurement. This has led to the discovery of dark energy, the mysterious force causing the expansion of the universe to accelerate. Without probing the cosmic frontier, we might still believe that the universe's expansion was slowing down under the pull of gravity, rather than speeding up toward an unknown fate. The edge also helps us test fundamental physics. The extreme conditions of the early universe, incredibly high temperatures and densities, are impossible to reproduce in any Earth-based laboratory. But by studying ancient light, we can test theories about particle physics, quantum mechanics, and general relativity in regimes that would otherwise remain purely theoretical. Even the smallest deviation in the structure of the CMB or the distribution of distant galaxies could reveal new physics that overturns existing models. And then there's the question of fate. By understanding the expansion rate and the role of dark energy, we can begin to project the future evolution of the cosmos. Will it expand forever until galaxies fade beyond view, leading to a cold, dark heat death? Will dark energy change over time, perhaps reversing the expansion in a big crunch? Could exotic possibilities like a big rip tear apart even atoms in the far future? These questions are not idle speculation, they are testable, at least in part, through careful measurements of the edge. In short, the edge of the observable universe is like a cosmic Rosetta Stone. It holds clues to the beginning, middle, and end of everything. Studying it has already transformed our understanding of reality, and it will continue to do so as technology improves. Every new telescope, from Hubble to the James Webb Space Telescope and beyond, pushes the edge a little farther, adding new chapters to the story of existence. What's remarkable is that this pursuit is not just about cold data. It's about narrative, about piecing together the origin story of the cosmos and, by extension, our own. We live in a universe where the answers to the deepest questions are written in light that has traveled billions of years to reach us. The edge is not just the limit of sight, it's the meeting point between curiosity and the infinite. When we step back and truly consider humanity's place in the cosmos, the scale becomes almost impossible to wrap our minds around. Our entire planet, every mountain, ocean, city, and forest, all the moments of human history, all the triumphs and tragedies, every thought we've ever had, exist in one minuscule corner of what we call the observable universe. And that observable universe, vast beyond comprehension at roughly 93 billion light-years across, might itself be only the tiniest fragment of an even larger, perhaps infinite, reality. Think of the night sky. When you look up, you're seeing stars in our own galaxy, the Milky Way. That galaxy alone contains around 100 to 400 billion stars, each potentially with its own system of planets. And our Milky Way is just one of billions of galaxies in the observable universe. That means there are more stars in the universe than there are grains of sand on all the beaches of Earth. And yet, we live on a small rocky world orbiting a rather ordinary star in one of the spiral arms of a galaxy that is, on the grand cosmic scale, utterly unremarkable. The fact that we can know this is extraordinary. For most of human history, the universe was thought to be much smaller, perhaps the size of a local region of stars, or even just what could be seen with the naked eye. Only in the past century have we discovered that the Milky Way is just a drop in a vast cosmic ocean. This realization shifts our perspective dramatically. It humbles us by showing how physically insignificant we are, but it also elevates us because, against staggering odds, we are a part of the universe capable of becoming aware of itself. Now consider this: our patch of the universe is defined not by walls or borders, but by the finite speed of light and the finite age of the cosmos. The light we see from the most distant galaxies began its journey billions of years ago, long before Earth even existed. Beyond the limit of the observable universe, there are undoubtedly more galaxies, more stars, more planets, perhaps more wonders than we could ever catalogue. But because the universe is expanding, many of those regions are receding from us faster than light can bridge the gap. They are forever beyond our reach, not just physically, but informationally. They will never send us so much as a single photon. This means our place is not only small in space, but bounded in knowledge. We live in a bubble of visibility, not because the universe ends at its edge, but because the rest is forever hidden. And that raises an astonishing thought. What is happening in those unseen realms right now? Are there alien civilizations, vast structures, or phenomena unlike anything we've imagined? Or is much of it empty, dark, and lifeless? The truth is, we may never know, and that's part of the profound mystery of our existence. Our location is also cosmically random. There is no evidence to suggest our position in the universe is central, special, or favored. The laws of physics seem to be the same everywhere we've been able to observe. This principle, the cosmological principle, states that on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same no matter where you are. If that's true, then somewhere in the vast expanse there are countless observable universes from the perspective of other beings, each with its own bubble of light, none more privileged than ours. This perspective changes how we view ourselves. On one hand, it makes our achievements seem incredibly precious. All of our art, science, and culture have emerged from a tiny blue planet in a quiet corner of space. On the other hand, it challenges us to think beyond ourselves, to imagine what it means to be a civilization in a universe that may be without end, and in which we are an infinitesimal fraction. And yet, there is beauty in this smallness. It means that every human being shares a home in the same tiny pocket of the cosmos. We are passengers on the same small ship, drifting through an infinite sea. Our place in the universe is small, yes, but it's also singular. In all of the observable cosmos, there is only one Earth that we know of, only one cradle of life that has produced beings capable of wondering about their place at all. If we were to gather everything we've explored into a single sweeping picture, the story of the universe's edge becomes far clearer and far stranger than most people first imagine. There is no hard wall out there. No shimmering barrier, no cosmic fence, no great abyss where space simply stops. Instead, what we call the edge is really just the outer limit of what light has had time to reach us since the Big Bang, some 13.8 billion years ago. This limit, the boundary of the observable universe, is set not by the structure of space itself, but by time, motion, and the unyielding speed of light. The observable universe extends about 46 billion light-years in every direction from us, not because that's the true size of the cosmos, but because the universe has been expanding during the billions of years it took that ancient light to arrive. Beyond that limit, the universe almost certainly continues. In fact, the evidence points to the strong possibility that it may be infinite, stretching endlessly in all directions, containing an unimaginable number of galaxies, stars, and possibly even other forms of life. If it's not infinite, then it's likely finite but without boundaries, curving back on itself like the surface of a sphere, where traveling in one direction long enough could, in theory, bring you back to your starting point without ever encountering an edge. Expansion is the key to understanding all of this. Since Edwin Hubble's discovery in the 1920s, we've known that galaxies are not just sitting still in space. Space itself is stretching, carrying them away from one another. This stretching happens uniformly on large scales, so every observer in the universe would see the same pattern of distant galaxies receding. And because the expansion rate is accelerating due to dark energy, many regions of the universe are receding from us faster than light. This isn't breaking the rules of physics, it's simply a consequence of how space-time itself can grow. Those regions are beyond our reach forever, no matter how far into the future we look or how advanced our technology becomes. That's why the edge is not something we can visit. It's not a place, but a limit, like a cosmic horizon at sea. You can sail toward the horizon forever, but it will always remain out of reach, and beyond it lies more ocean that you can't see from your vantage point. Likewise, as time passes, light from slightly farther away does reach us, and our observable bubble slowly grows. Yet the expansion ensures that there will always be far-off regions that remain permanently hidden, slipping away faster than any signal could bridge the gap. And so, our observable universe is a small, precious patch of something vastly larger, perhaps without end. The ultimate truth may be that there is no final boundary, no outside, and no center. Just an ever-expanding tapestry of galaxies, with our tiny speck of existence woven into it. Maybe the edge is not a place at all. Not a destination marked on some cosmic map, not a final point we could ever stand upon and gaze beyond. Instead, perhaps the edge is a concept, a mirror reflecting the limits of our understanding. It's a gentle but unyielding reminder that for all we've learned, the vast majority of the universe remains hidden from our sight, our instruments, and even our imagination. Think about the night sky you see when you look up from your backyard, a mountain summit, or the deck of a ship at sea. Every point of light you notice, every star, every galaxy, is only a whisper from the nearby portions of the universe. It's a comforting illusion that we can see everything, when in truth, what we see is like a small candle in a cathedral so large that its walls are lost in darkness. And beyond that darkness lies more space, more time, and perhaps more worlds than any mind could number. The edge challenges us in the best possible way. It tells us, there is more. More to measure, more to map, more to imagine. It says that our journey through knowledge will never truly end, because the universe is not something to be finished, but something to be lived with, a mystery to be explored in perpetuity. It humbles us by showing that our cosmic address is just one line in an infinite directory, and it inspires us by revealing that there are uncounted chapters of the universe's story still unwritten in our understanding. We are the only known species, in the only known corner of the cosmos, able to ask questions about the whole. That in itself is astonishing. On this small blue planet, orbiting an average star in an average galaxy, life has grown curious enough to stare into the abyss and wonder not only what is there, but why there is anything at all. Perhaps, then, the edge is a kind of invitation. Not a boundary telling us stop, but a horizon whispering, come find me. A point where the known world hands us a map with blank spaces and says, your turn. And maybe the true beauty of the universe is that there will always be more blank spaces, no matter how far we go. So the edge is not a wall, and it is not an ending. It is a promise, that wonder itself will never run out, that there will always be questions left to ask, that there is still so much more waiting to be discovered. And maybe, just maybe, that's the most exciting truth of all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.